Welcome to another module in this massive open online course on probability and random variables for wireless communication. In the previous module, we have looked at the concepts of mean and variance of a random variable x. Let us now look at a simple application of this mean and variance of a random variable. So, let us look at an application of in a wireless. Let us look at the application in a wireless scenario for these concepts, our mean and variance. Remember, mean was denoted by mu, the variance of random variable x by sigma x square. We can also denote this by mu subscript x to denote that this is the mean of the random variable x. Okay. Now, as we have already familiar with the typical wireless scenario. So, in a typical wireless scenario, let us say I have a base station. So, this is my base station in a typical wireless scenario. This is something that we have already described in the previous modules. So, I am going to be brief. I have a base station which is transmitting to the mobile. So, there is a direct line of sight component, a signal which goes from the base station to the mobile, and because of reflectors there are several scatter components because of obstructions such as buildings etc. in the wireless environment. There are several non line of sight. For instance, let us take an environment that corresponds to trees. There are several non line of sight components. So, I have non line of sight components as well. So, basically what we have in a wireless environment is, if I look at the signal that is transmitted from the base station to the mobile, because there is no guided medium, it is not there is no guiding medium for the propagation of the signal. There is a direct line of sight component between the transmitter and receiver, and several non line of sight components which arise from the reflections of objects such as the trees, buildings, large objects which are in the wireless environment. Therefore, there are multiple signal copies, right. So, at the receiver there are multiple signal copies. These signal copies are arriving with various delays. So, at the receiver in a wireless environment, at the receiver we have, what do we have? We have multiple signal copies and these signal copies are arriving with different delays. Because if you look at this figure, the distances of propagation of these different paths are different, right. So, if you look at the figure, these different multipath components, they traverse different distances. One is reflected from a building, another is reflected from a tree, one is the line of sight which is the shortest distance, which means the shortest delay. So, these different signal components are arriving at the receiver with different delays, which means the power is going to arrive at the receiver at corresponding to the different delays. So, the different signals, the different reflected components, reflected signal components arrive with different amounts of power. So, the power arrives at the receiver with various delays. So, the power in, so different signal components arrive at different, and these different signal components have different power. Have these different signal components have different power. So, basically the power, one can say that the power is arriving with different delays. So, one can say power is arriving the power is arriving with different delays, and therefore, in a wireless communication system we consider what is known as a power profile. We consider what is known as a power profile. So, what is my power profile? So, this is my power profile or my multipath power profile. This is also known as a multipath power profile, which gives the distribution of power versus delay. So, if this is my tau, this is my f of tau, basically it gives the distribution So, the power in these multipath signal components, multiple signal components is arriving with different delays, right. So, if I look at the power profile of the wireless channel, what that is? It gives the distribution of the power of the multipath wireless channel as a function of the delay. This is known as the power profile, or this is known as the multipath power profile. Based on this multipath power profile, one can compute parameters similar to what we did for the random variable, that is we can compute the average delay and we can also compute the variance of the delay. These two properties are very important for a wireless communication system. So, based on the power profile, the multipath power profile, one can compute the average delay and the variance of the delay. So, we can compute based on the power profile one can compute the average delay and one can also compute the variance of the delay. For instance, let us look at a typical power profile. The typical power profile is given over here. You can see the typical power profile. The typical power profile is exponential in nature. Typical wireless power profile is similar to what we had seen for the exponential random variable. This is exponentially. The typical multipath power profile in a wireless communication scenario, in a multipath wireless communication scenario, is exponential in nature. This is the exponential distribution that we had seen in the previous modules. Therefore, if we look at the typical power profile f of t that is equal to beta e to the power of minus beta t. So, this is my exponential power profile . This is my exponential power profile, and where beta is a parameter, that is also what we had seen yesterday. Beta, this is a parameter. So, this is the power profile, this is my multipath power profile, this is the multipath power profile. And now therefore, from this multipath power profile one can compute things such as the average delay. The average delay or the mean delay, that as we have said before, is integral 0 to infinity x or tau times f of tau d tau. This is integral 0 to infinity tau times f of tau d tau. It has to be integral, the definition is integral minus infinity to infinity. However, this power profile we are assuming it is exponential, which means remember exponential random variable is non-zero only for tau greater than or equal to 0. For tau less than or equal to 0, it is 0. So, this is integral 0 to infinity tau f of tau times d tau. So, therefore, the average delay, which is also can be denoted by tau bar, equals 0 to infinity tau beta e to the power of minus beta tau d tau. Now, let us use integration by parts. I can first integrate beta e to the power of minus beta tau. So, that will be minus tau minus tau. So, integral beta e to the power of minus beta tau is minus e to the power of minus beta tau. Therefore, using integral by parts, I have plus integral 0 to infinity. Of course, this is between the limits 0 to infinity, integral 0 to infinity. Now, differentiate tau. So, e to the power of minus beta tau d tau. Now, if you look at this quantity minus tau e to the power of minus b tau between the limits infinity to 0, at infinity e to the power of minus beta tau is 0, at 0 tau is 0. So, this quantity is basically this is 0. So, I am basically left with integral 0 to infinity e to the power of minus beta tau d tau, which is basically equal to, now if I simplify this, this is basically equal to minus 1 over beta e to the power of minus beta tau between the limit 0 to infinity. At infinity e to the power of minus beta tau is 0, at 0 e to the power of minus beta tau is 1. So, therefore, this is 1 over beta. Therefore, we can say that the average delay corresponding to this exponential multipath. What is tau bar? So, we have evaluated tau bar. Tau bar is average delay corresponding to the exponential power profile beta e to the power of minus beta tau. So, we are saying corresponding to the exponential power profile in the multipath wireless channel, where f of tau equals beta e to the power of minus beta tau, the average delay tau bar, which is integral 0 to infinity tau f of tau d tau is 1 over beta. Now, let us look at the standard deviation. Let us look at the standard deviation of this delay. The standard deviation of this delay, or the variance, I am sorry, not the standard deviation, let us look at the variance of this delay. Let us look at the variance of this delay. The variance is given as, well, we have sigma tau square equals expected value of tau minus tau bar square, which is also equal to, as we had remember proved in the last lecture, expected value of tau square minus tau bar square. We have derived the expression of tau bar, the mean is 1 over beta, that is expected value of tau square minus 1 over beta square. Now, let us evaluate the expression expected tau square. So, we are shown that the variance sigma tau square is expected value of tau square, the average of the square of the delay minus the average delay square, that is 1 over beta square. Now, let us evaluate expected value of tau square, that is the average of the square of the delay. So, the average of the square of the delay, expected value of tau square is nothing but integral 0 to infinity tau square beta e to the power of minus beta tau d tau. Once again, using integration by parts, I have integrating beta e to the power of minus beta tau minus tau square e to the power of minus beta tau plus, now differentiating tau square, this is 2 tau e to the power of minus beta tau d tau, and of course, the first one is between the limit 0 to infinity. Now, if I look at this part again, at infinity e to the power of minus beta tau is 0, at 0 tau square is 0. So, this is basically 0. So, I have between infinity to infinity, what remains is integral between 0 to infinity 2 tau e to the power of minus beta tau. Now, what I am going to do here is I am going to divide and multiply by beta. So, I have 2 over beta integral 0 to infinity 2 or tau beta e to the power of minus beta tau d tau. So, dividing and multiplying by beta. Now, if you look at this, this is tau, f of tau beta e to the power of minus beta tau is f of tau. So, this is basically 2 over beta integral 0 to infinity tau f of tau d tau, because f of tau is beta e to the power of minus beta tau, and this is basically, this integral is nothing but the mean, which is mu equals 1 over beta. Therefore, I have the expected value of tau square equals 2 over beta times 1 over equals 2 over beta 1 over beta equals 2 over beta square. This is 2 over beta square. So, expected value of tau square is basically 2 over beta square. Okay. So, that is what we have derived. Now, one can derive the mean as follows. Now, one can derive the variance as follows: sigma tau square is basically expected value of tau square minus the mean square, which is 1 over beta square, which is equal to 2 over beta square minus 1 over beta square, which is basically equal to 1 over beta square. So, sigma tau square equals 1 over beta square. The variance of the delay is 1 over beta square. Now, if we look at the sigma tau, that is the standard deviation, sigma tau square is the variance, sigma tau is the standard deviation of the delay. Now, sigma tau equals obviously square root of sigma tau square, which is equal to 1 over, this is equal to 1 over beta. So, we have the standard deviation sigma tau equals 1 over beta, and this is an important parameter in wireless communication. This is also the delay, RMS delay spread. This is known as the root mean square delay spread, or this is also known as the RMS delay spread of the wireless channel. This is also known as the RMS, this is also known as the RMS delay spread of the wireless channel, which is equal to 1 over beta. So, what we have derived is that sigma tau, which is the standard deviation of this delay, which is the square root of the variance sigma tau square, is equal to 1 over beta. This is an important parameter in wireless communication because it denotes the RMS delay. It tells you what is the delay spread, what is the spread of time over which the signal energy is arriving at the receiver. This is a very important parameter in a wireless communication system. This is known as the RMS delay spread. This is a metric to measure the delay spread. It stands for root mean square delay spread. So, what we have seen in this module is we have seen an important application of the mean and variance of the random variable in the context of wireless communication for a given multipath power profile, that is the power, that is the spread of power, the distribution of power versus delay. We have seen what is the average delay, which is given by the mean, the variance of the delay, and the square root of the variance of the standard deviation of the delay, which is known as the RMS delay spread of the wireless channel. So, we will stop this module over here and we will look at other aspects in the subsequent modules. Thank you very much.